So hi, I'm Denis. I'm a performance engineer at Meta. And like my manager asked me to say that we're hiring. If in the States, we're hiring for some really fun stuff. So if you want to know about that, talk to me. Anyways, so as you can see, there are two people on the title card. Like, and this is 3 hours talk for two people would be good. Fortunately, things happen, and Joel couldn't make it. So he recorded an intro video for me where he says nice things about me and like how he trusts me to speak here and all that stuff. And now we cannot make the sound work. So I have to ignore that intro video, but trust me, he says nice things. Okay. This is the video again. All right. There's the slides. So the slides are at tinyurl.com/jfdy2025. And this is PT1. It will be on the slide for a second, and if you need me to repeat, like I can repeat that. What are we going to talk about? SIMD ranges are coming, right? Standard SIMD has been standardized, and very soon, some of the same people or some different people will come and say, hey, we should do the ranges thing, right? And Joel and I and some other people, we have an implementation of SIMD ranges. We have some algorithms, some views, some combinations of those. So we have some knowledge to share, mostly about the problems, right? We will talk about our solutions to them. I don't particularly care if you decide, the standard decides to do the same solutions or different solutions, but the questions should be answered. Yeah, so how many people know SIMD though? Like how many people written some SIMD? That's not bad, that's very good. I assumed less, but we still need to teach you some SIMD to be on the same point. I will be talking about standard SIMD a little bit here. I'm going to mention that we showed this to Matthias Kretz, who was one of the original people pushing for standard SIMD. And I will be trying to reproduce his opinion on things where we disagree. Right. As a step one, let's agree for this talk on a rule. As a rule is no magic compiler. Right? So a lot of the time when people talk about the standards, they're like, oh, here we're going to specify this arbitrary condition, and because compiler will know about this arbitrary conditions, they will be able to optimize things. And I don't mind compiler optimizing things, but there's already an approach to write SIMD like that, and it's called standard unseek, standard execution unseek, where you kind of pass special execution policy to your algorithms and they get vectorized. If you look at the implementations of standard unseek that at least I found, they kind of try to rely on magic compiler doing the right thing. Sometimes there will be like writing loops in a certain ways or attaching special pragmas. And, this is good stuff. I'm happy for them to continue. So far, the results are not really there. There is some, but the code gen quality of what I have seen has not been up to what I would like. So for this talk, let's agree. If the compilers today don't do it, we have to kind of collectively agree that they will be able to do it in the future. Okay. With this, let's explain some SIMD. I'm going to start with memcmp, memchar, strlen, so libc functions. Then we're going to do reduce. We're going to talk about some structs. How do you handle complex types? I'm going to then do min element. And finally, we can look at copy if. All right. So standard memcmp. Standard memcmp is a libc function. You take two arrays. You compare, you return a negative number, 0, or a positive number, depending on how they compared. If I was writing my own libc using C++ standard library, which standard algorithms could I use for this?
Mismatch.
Sorry?
Mismatch.
Mismatch, perfect. You're actually the first person who I think ever mentioned mismatch, but that's the correct answer. Yeah, there's another one. Yeah?
Findif.
Findif with a zip view, yes, but I want another one. Equals to Johnny Bull. You want like a number. There is an algorithm called lexicographical compare freeway from the C++ 20s that uses operator spaceship. But anyways, if you take memcmp, if you look at CPP reference for, well, let's say mismatch, because that's the algorithm we're going to use, you'll see something like this. You take two ranges byte by byte, and you compare them, right? That's what the code will be. Okay, in standard C++ today, if we wanted to improve it, how could we improve it? Like, assuming compiler is not magic here, like it didn't do anything crazy. It's not a very trick question. So. Well, on a single core.
Let's load 64 bits.
64 bits.
Yeah.
Thank you, Elliot, who listened to some version of this before. That's not nice, but okay. So you can use int64. And it's a bit tricky because, like, for example, your range might not be divisible by 8, right? And your pointers might not be aligned to 8 bytes. And in the standard, if you load int64, the pointer has to be aligned to int64. But that one we actually can solve by using memcpI. So this is, if you want to do an unaligned load in C++ today, you memcpI. And every compiler will generate you the correct instruction here. So you memcpI to address of a local variable. Okay, so there is a little bit of a tail left after we did this. Oh, let's figure that out. How do we compare 16 bytes? It's not a trick question. Standard C++, how do we compare 16 bytes? No. We're writing standard memcompare. That's not going to finish then. Like, how do we compare? Like, okay, so.
STD byte.
Sorry?
STD byte for 2 times, right?
Well, this is 16 bytes, not bits.
Oh, I'm sorry.
So, but you're right, in 64s 2 times.
Yeah.
Because that's not a trick question. Now the trick question, 15 bytes.
Okay. 164-bit, 132-bit, 1.
Yeah, you can, but you can do better. Any other options?
2 64 bits overlap.
Yes.
Oh.
Very good. Have you seen that? Or did you just figure? Like, if you figure that out, you're smarter than me. I have seen that other people do it. I'm like, that's very cool. Finally, so this works all the way up to 7 bytes. So at 7 bytes, you cannot longer load 8 bytes. If this looks esoteric, it's actually not. So if you look inside standard memcmp, the actual ASM, right, it will do something like this. All right. So on the right, on the red one, the big one, right? This is whatever I copied from from CPP reference. And this is something I wrote using int64s. And the difference is 8 times. Compiler didn't do it for me, right? Anybody can guess why? Well, one thing I'll give you, it's not implemented well enough. Would be good if it's possible to do. There's another problem though. And the problem is kind of like this. This is not an equivalent transformation, strictly speaking, because we have while, for I 0 to n, right? We go and compare things. But what compiler doesn't know is that n is reachable. What it sees is you have a loop that interrupts on 2 conditions. 1, you found the mismatch. 2, you reached n. Nobody told you that n is reachable. Think about strn len, right? Strn len has a limit, but nobody told you that n is reachable. That is a problem that can be worked around. We'll mention it later. Anyways, so this is actually STD mismatch. STD mismatch is another 2x faster. And this is standard memcmp, which is another 2x faster than STD mismatch. Let me mention that this STD mismatch improvement is a very recent work done by Nicholas Clauser. It was merged into libc++ like last year. So very recent stuff. About this difference between mismatch and memcmp, I will talk later. But the main difference here is memcmp to the scalar code, to the normal loop, right? And that difference is about 32 times. But how do they do it? Well, actually, they're not doing anything that's different from what we did with ints, except, we used ints. Ints are not designed to be many bytes. We have special registers. On my machine, I have 32-byte registers, and so I get a 32-byte speedup. Okay. How do we access those registers? In this talk, I'm going to be using Eve library. So Eve library is on GitHub. It's Boost license C++ 20. Right, and it's developed by Joël Falcou, my co-presenter who couldn't make it, Jean-Thierry Lapreste, Alexis Owen, and me. And we have a mismatch. And as we discussed, we can use mismatch to implement memcmp. So let's have a look at the numbers. So how does that compare to the standard? It is almost as good as standard memcmp. The difference here, although very annoying to me, is not that big. Right. I may or may not know why it is there. We're not going to go into that, but the main thing is it is still beating STD mismatch, so hopefully you believe me that I know what I'm talking about. This is Apple result. This is the only place I show Apple results, right? And this is on M2. We actually beat STD memcmp, which makes me immensely proud. That is almost a, 30% for sure difference. And you see standard mismatch is very bad because the optimization didn't come there yet. The optimization of the standard library. Okay. How are we doing? Any questions so far? All right. Let's look at the interface of mismatch. How does Eve mismatch look? So here I have a co-mismatch. In a standard mismatch, it has two interfaces. You have three iterators, like the C++ 19 stuff. And you have the ranges stuff, which accepts two sets of ranges. This is our equivalent of the three iterators interface. So Eve is ranges first, because I accept, so we here accept a span and an iterator, and I pass a span instead of a pair. The reason why we're ranges first as opposed to being iterators first is because sometimes a range contains more information than iterator would. Think about the vector. A vector can have an allocator, and if it's, let's say, allocators that we provided, we know that it will guarantee certain alignment, right? And then I can extract it. But if it's just a vector iterator, I am out of luck because it can be anywhere. A second thing that may be noticeable here is that the return type, I do something finicky with the return type. Like the standard mismatch returns a pair, and we return something. This something is a zip iterator. So we return you a position into two ranges and two parallel ranges, and we think that zip is a better representation of that, just because we think it's convenient. I'm not necessarily recommending that the standard does it. That's not my concern. This is just what we do. If that was all there is to it, it's not that interesting. The interesting thing is to pass a predicate. So let's have a look how that looks. So here, I want to compare floats, and I want to compare floats with an epsilon. So I call mismatch in exactly the same way, but except I pass a predicate. This predicate accepts two wide of float. Wide of float is our abstractions on top of a register. So on my machine, this will be 8 floating point values, right? If you compile on your, it can be 4 floating point values or 16, something like that. And then we do our comparisons. We do absolute value of a difference is less than epsilon. Any questions about this?
So then for flowing, we're assuming, when we're saying mismatch, they are closer than just...
Yes. Okay. So the mismatch accepts equals as a predicate. Okay. So it's equality function. I will point out this operator less here. This operator less was a big point of controversy when standardizing SIMD stuff, because it doesn't return you a Boolean value. It returns you, in this case, 8 Boolean values for each of the pairs of floating point. Anybody feels really upset about it? Okay.
Because I was the one who wrote the paper.
Perfect. At the end of the second talk, where everybody's tired, there is a slide about it. So
the mismatch, even it's an array. Array. It is a bit set, something. It's a representation of 8 different Boolean values. Do all of them have to be true for it?
No. Only. Sorry.
Or
The mismatch, it's a predicate that returns you 8 booleans. Mismatch will look and will find one position that, like one true will be enough for interruptions.
Cool. And then the iterator return would be that position. Of
Yes.
that. Okay.
Is this exactly the same? It's just a predicate looks differently. Perfect. Good point. All right. So I keep saying on my machine, right? This stuff is not terribly portable. Depending on the platform, you will have different extensions available. And like new Intel CPU comes out, it might have new instructions. So this is just some sets that we were looking at. Most of them are supported in Eve. When I show you numbers, this is this stuff. This is AVX2. It's like 10, 15 years old. Should be on your x86 computer for sure. If you just write O3, just default compilation, this stuff only is available. It's like super, super old. On Apple, the numbers I showed you are with this family of extensions, SIMD. I'm not going to talk to you that much about compilation, but I'm going to mention this is important. There's a difference between compiling correctly and compiling whatever, just saying O3. It's the same algorithm, written in exactly the same way. It's going to be a 2x difference in performance. Okay. So, hopefully, seems like mismatch does the right thing. What's inside? And inside is actually just find if. So Eve is a ranges library, that's why I'm here. And it makes a lot of sense to implement mismatch as a find if a position with a zip. So let's instead write a find. This is a simplified version of kind of like the core of the find loop. So this function checks on my machine 32 bytes for a needle. Okay. I accept a pointer where the 32 bytes will be, and I accept the needle. Step 1, I need a SIMD register, right? So I declare my type def for a while. Then we load from the pointer. So in the example here, I just show you 1, 2, 3, 4. In reality, it will be 32 bytes, yeah?
And the convention for Eve wide is 4, or?
Wide is whatever's a natively correct thing. So in my machine here, it's going to be 32 bytes. So it's going to be 32 numbers.
Okay.
I'm just showing 4 because I don't want to type 32 values. It's not helpful.
Okay, thank you.
Yeah. Second thing I have is I want to compare this to a needle. So I need to convert needle into a wide. This is an operation called the broadcast. So what it does, it takes a needle and writes it 32 times. So you kind of like in each of the element, or as we in SIMD call them, lanes. So this is just slideware, FYI. This broadcast would be done outside of the loop. Like you just broadcast the needle. You don't need to do it on every iteration of the loop. Okay. Then we do the comparison. And as I mentioned, comparison returns you not just one Boolean, but a bunch. So here we have whatever, like false, true, false, false. And after that, I am calling a special reduction function called first true, which takes this logical of this false, true, false, false, and gives me a position of the first true element. So in this case, it's going to be 1. If there is no matches, it returns an optional, so that will be a null opt. Then we check, okay, no matches, go to the next 32 byte register. If there are some matches, there's a way to return, we return whatever, where the position of the match was. I will give you a moment to look at it so that you can ask me a question and see what you don't understand.
I guess I'm not getting. Oh, it's a reference. F is a reference.
F is a reference. Yeah, that's a confusing point.
Yeah.
So how do we return pointer from here? F is a reference. It's just
Right.
the way I wrote it. I'm sorry. I don't know how to do it differently.
And is there something outside the logic that makes sure that F points to the valid side of Y?
So this checks just 32 bytes. So this is the way you check 32 bytes. So on side you would have a loop that goes.
Understands how large it is. Okay.
Yeah.
Cool.
Anything else about this? It's the biggest piece of code in these slides. All right, perfect. So how does this compare to standard? I've spent my Friday replacing standard SIMD with standard data par SIMD in all the places. Hopefully I didn't miss anything. But there's again trying to introduce namespace. So now this is called standard data par and then all the operations. So what we call wide is called standard data par SIMD. Okay. What we call load, standard calls unchecked load, and it accepts a range. So we let's have a look here. We load it from a pointer. What standard wants you to do is on top of this pointer here, it wants you to pass where the end of your array is, so that in debug mode it can assert that you didn't override it. The logical is called SIMD mask. The operator overloads are exactly the same operator overloads that upset everybody. Not everybody.
No, just me.
Okay, perfect. And finally, what we call first true is split into two functions. One of them is any of, so just is there a match or not? And the other returns you, called the reduced mean index, which returns you the position of the first true. I'm perfectly fine with all of that, except like reduced mean index, I don't think is a very helpful name. But that's me. Okay. So let's look numbers. So this is standard find if. I use find if here so that I pass a predicate and the compiler doesn't do anything fancy. All right. This is what we wrote, and it's about 20 times faster. And this is standard find. Standard find is another 2x faster than what we did. How does it happen? So standard find under the hood for chars on libc we'll call memchar, which is a libc function that is written correctly. And what it does some unrolling. This is the same difference we saw before with mismatch and memcmp being different, with us being Apple. It's all about unrolling, right? Conceptually, you have a operation that says sometimes your loop are bounded by the number of instructions executed. So you can do 4 instructions per cycle, let's say, right? And so sometimes, in order to get faster, what you need to do is you need to do less instructions. Unrolling is a very good tool to use less instructions. Here's what we do. We take 4 registers. Each of them is like 32 bytes. We test all of them against the needle. We do an OR, and we do another OR. And only after that, we'll do an any. So this way, we checked 128 bytes in substantially less instructions that would take you to implement those checked individually. This will give us almost the performance of standard find. I don't know what this difference is, but I believe it is real, and it's very frustrating. But 5%, maybe 10. Okay. Any questions about unrolling stuff? Let's look at some numbers, because those numbers is comparing against memchar, and please don't write in memchar outside of fun projects, right? The interesting part is what if we give it the predicate, and then how do we actually speed up compared to scalar code like a regular C++ code? So this is a SIMD benchmark. The SIMD benchmark I usually do in terms of size, because the SIMD register doesn't care about the type. You have 32 bytes. And it doesn't care if it is chars or ints, the time it takes to be the same. So here I have 10,000 bytes, and I benchmark, and you see the find for chars, for shorts, and for ints is the same time, just depending on size. The speed up for chars is about, 30-something times. For shorts, this is going to be more than 16 times. I don't want to do the math. And for ints, this is about 9 times speed up. There's an interesting implication to this one. And the implication is like this. In a normal situation, you don't care about the byte size. You care about the number of elements, right? But what happens is, in the same number of bytes, you put half as many elements if there are integers and not shorts. So in reality, what this means, if in terms of elements, A benchmark, like ints are twice as slow as shorts. It's processed the same size. I don't have the benchmark. It's really hard to generate from my stuff, but it's the same. They have the same time, but the number of elements processed is twice as many in terms of shorts. So SIMD cares about types a great deal. You want to have your types as small as it reasonably possible. Okay. Yes?
So I assume that depends on whether the data is like already in the cache or not, right? Because if you're hitting memory bandwidth, then you'll be slower, like you'll be waiting on fetching more data if you're doing bigger work.
Yes. So the comment is that if you're cache bound, yes. If you're downloading data from the internet, you will probably also wait longer. Like, this matters in prod. Like, I don't know. If your data is smaller, it is more cache friendly.
Also, it's just a sequential loop. It'll be prefetched.
Yeah, but it's a valid consideration. Okay, let's talk about strlen. And strlen is a weird one. I actually started my SIMD journey trying to understand how in the world they can vectorize strlen. And here is how. They look at the fact that allocations on your machine are happening in pages. So if you have a byte somewhere, it actually means that your whole page is allocated to you. And there's a consequence from it, that aligned addresses are safe. I'm going to explain how that works. So let's have a look. So this is a string somewhere in memory. This is a page. Let's add some addresses to the thing. So we have, the beginning and the end of the page are going to be aligned to 4 kilobytes. And this is my string. It's somewhere. What if I take this string and I align the address to 32 bytes, because 32 bytes is my register size? Then so happens that the differences become divisible by 32. Like, this is divisible by 32, this is divisible by 32. I subtract them, like the result is divisible by 32. And what that means, if I go from this address in the chunks of 32 bytes, I am either going to be entirely in this page or entirely on the next page. And that means either my string stopped on this page, or my string continued to the next page, and I'm just safe to continue loading. Does this make sense? Thank you for the thumbs up. I didn't come up with it. It's very cool. Right? So now we can remove everything about the addresses, and we can just start writing code. So what we're going to do is we're going to align the address, load the register. In theory, we could just try to check for the needle here, right, for the 0. However, we have this little bit in the beginning where they, like, for example, a previous string might be, and there can be a 0 in there. So this is why all the functions in Eve allow you to skip some elements. Tell, I don't care about this elements here, so I can ignore like everything between aligned S and S. Right, so if there's a 0 here, we will not return true. Make sense? Then we take the next register, and here's going to be our distance. This is our result. I wanted to talk about standard SIMD and standardization. There is 0 chance this makes standard, right, Jeff?
Oh, what? Parallel straight line?
Yeah.
I don't think you need to say anything, right? I mean, the vendor can do it under the hood, right?
The strlen is fine, but if you wanted to write it in your code, you can't really make it. I don't think you can standardize reading outside of the array boundaries and things like that.
Oh, I see what you're getting at.
Yeah.
Is platform specific to Linux?
The pages stuff, no. The pages stuff was everywhere, but like it's just
behavior.
It's undefined behavior for sure, and trying to push it through the standard sounds impossible. However, there's a reason why we're talking about. The reason is that this is a ridiculously good tail handling technique. Let's have a look. So this is an Eve find for 40 bytes. 40 bytes is nothing, right? But however, still for 40 bytes, Eve find beats standard find by a factor of 10. Okay, and even for integers, so this is searching 10 integers. Eve find will give you roughly the same performance as standard find. This is very good. There is in certain overheads with just starting up the SIMD algorithm, like the operation of broadcasting, for example, that I showed you, is quite expensive. And so if the compiler somehow under the hood can generate this tail handling for you, this would be very good. So if we do it because we kind of don't care that much about this. So a few conclusions here. We saw that compilation target is important. We saw the 2x difference. We saw that types are important. I want to highlight here that we cannot just do for each. Even for a simple algorithm as find, we already needed to unroll it, and we needed to do it ourselves. Compiler couldn't do it for us. It's not a for each. Just we saw the overlapping tail handling, where we did 2 overlapping registers. We saw the aligned load tail handling when we used the fact that loading from an aligned address was safe. And finally, we saw that in case of, let's say, strlen, some values in the register were garbage values. Like we could not possibly control what they are. We loaded them from just memory. Okay. Any questions so far? Yeah?
So I think you can get close to this in a standard compliant way, which is to handle the beginning chunk manually and then the last chunk manually so that you don't even read outside of it. Just read every byte or every word or something.
You mean scalar thing?
Scalar or like, every short versus, and then if you're going to do longs, like do that.
Like the tail handling, I have a really big section in the second part. Tail handling is one of the most important part in SIMD algorithms design. We will talk about that and let's discuss it there. But you're right. So a couple of acknowledgements here. So Stephen Cannon had a really good write-up on how to do strlen on Stack Overflow. Most of the things we learned here was just from reading glibc. So we appreciate those guys. So standard mismatch was recently improved by Nicholas Klauser. Fantastic work. And with this, let's go to reduce. Let's acknowledge that reduce is auto-vectorized by every compiler that's available to you. Maybe you need a pragma for like floating points to tell that it can change the operations around it, but generally speaking, it just works. But it's very instructive as far as examples go. There are 2 important cases in reduce. There's a reduction to the same type, and there is a reduction to a different type. Like imagine if you want to add up shorts. There's a chance that your sum of a short will overflow. So you want to use a bigger type to do the additions. Let's do the same type first. This is the interface that if provides for reductions. You want to accept a range, or accept a pair of operation and a 0. This together is a monoid in mathematicals. Like when you have an operation that is associative, commutative, and it has a 0, that's a monoid. And we have an initial value. Okay, so this is our array, and we're gonna have 4 accumulators of whatever. Let's say this is integers, so this is 4 registers of integers initialized to 0. I'm gonna do aligned tails handling technique, so I'm gonna load from aligned address, replace this with zeros, add it to the first register, to the first accumulator, second one adds to the second accumulator, third to the third, fourth to the fourth. Right. Then we add all of them together, and finally we reduce the SIMD register to a single value. So why do we need the 0? We need the 0 to replace garbage values, and we needed the 0 to initialize the accumulators. I believe you can get away for reduction algorithm specifically without a 0. It's going to be annoying. The code will suffer for it, but I think you can make it work. However, for other SIMD algorithms like inclusive scan, there is no way of getting rid of 0. So in if we just accepted the 0 is going to be a requirement for our operation. The second thing I want to mention here is why do we need commutative and associative? And basically because we add elements in absolutely random order, right? So I took an element from here, I added here. And then I took an element from here and I added here. And then an element from here will go again to the first register. They completely messed up. So you really need the operation to support it. Okay. So let's talk about how we take a register and reduce that register to a single value. So this is our register, A, B, C, D. We're going to use this fundamental building block of SIMD algorithms called shuffle. Shuffle is moving elements around in a register, and in our case, it's compile time known indexed, right? So in this case, what I'm going to do is I'm going to take the elements from the second part and swap the halves. Right? So I get C, D, A, B. I add them together, I get A plus C, B plus D, A plus C, B plus D. Right? Now I'm going to do the same in each half, and this is going to give me A plus B plus C plus D. This is sometimes known as a butterfly pattern because, you know, and in this algorithm, it doesn't important because we do just once, but generally speaking, this is like logarithmic complexity to add n elements as opposed to linear complexity to add n elements. So sometimes even using this in a loop repeatedly can be a speed up compared to scalar curve. Now let's look at a different type. So what if we want to add, let's say, shorts to ints? So we're going to have our 4 accumulators worth of ints. And then instead of using I'm going to load registers worth of shorts, but instead of loading all the 32 bytes worth of shorts, I'm just going to load 16. And then I'm going to convert them to 32. So that basically do the conversion operation from shorts to ints. So this hopefully very clearly illustrates why you have only half the speed for ints compared to shorts, because you only process 16 bytes in this case as opposed to 32 bytes at a time. Okay. Let's look at some numbers. So as I mentioned, standard reduce is always vectorized. So this is reducing chars. So we're adding up chars. If we add up chars to chars, then if is about 20% faster than the standard library. For chars to shorts, chars to int, it gives me the same results. For shorts, short to short, again, if is a little bit faster, 20%. And then for short to int is about the same. And finally, for int to int, so the same 20% difference remains, but roughly is similar. I am not sure where the difference comes from. So let's compare to standard data par. So we have a function to reduce a SIMD register. Standard has a function to reduce a SIMD register, exactly the same function. Standard doesn't have a shuffle yet. So there's a paper that proposes some shuffles, but not in the standard as is. So you cannot write your own reduce function today. What we have known as convert, to convert from chars to shorts, there are a few options. So the one that's the most similar to our convert is called SIMD cast. So you SIMD cast from a register of 8 shorts to a register of 8 ints. There's also an explicit a constructor, and it's implicit if you construct up. So if you want to construct 8 ints from 8 shorts, it's implicit. If you want to construct down, so construct shorts from ints, that will have to be explicit. And finally, there is also a SIMD flag convert. So when you load elements, you can automatically say, hey, I would like to load this and convert it at the same time to int. I'm just going to mention it. So they do it for the interface benefits. But generally speaking, I am not aware of any performance benefits that would come from having this SIMD flag, as opposed to loading and then converting. Okay. Any questions about this so far? So we saw shuffles. We saw how reduce has a different interface to standard reduce, because standard reduce does not have a 0. And in fact, when it's vectorized, like the compiler just magically understands, oh, you have an add, then I'm going to generate you a 0. If you have a min, it's going to do, I don't remember, like maybe maximum integer or something like that. So this is why, for example, I'm not a big fan of policy proposals. So there's proposals to do like, is the same as standard bar unseek, right? Standard bar whatever. There's the standard SIMD where you would get SIMD registers. I am a bit objecting to that because I believe the interfaces should be different, and I do not like, and it's going to be weird. And finally, we saw some mixing types. We mixed shorts and ints. So that brings us to writing structs and types. How are we doing? Yeah.
Just a comment on the previous. I don't think you need commutativity for the reuse, do you?
I'm pretty sure you do. So if you don't have a commutativity, what happens is
You could just always reduce to the right, for example.
no, because you add lane by lane.
Yeah.
So you have element 1 goes. So let's say you have one sum register with 4 elements. The zeros element goes into here, and the 5th element goes into here. So you just put 5th element before 4th, 3rd, and 2nd.
I see.
It's a reordered mod 4. So you need commutativity.
Yeah.
If it's not, I can, okay.
No, it makes sense, like what you're doing. It makes sense. I'm just thinking, how much does that give you? But like, yes, like if you
It gives you 32 times speed up from like 8 times speed up for integers, because you can use SIMD register, otherwise you cannot use SIMD register.
I need to think about it. Yeah, sorry.
No worries. Yeah, I appreciate. This is after lunch session, and the last one is going to be the sleepy session. Like so, so this is no session where you're going to be functioning for it.
Well, what I'll say quickly is, if you want to see the difference, you can go in Godbolt, write a simple for loop, and then compile, like floating point, and then compile with the flag that allows reordering or without the flag. And then you can see how the simple.
Yeah, no, that doesn't prove anything, because the compiler could just not do the right thing. I am not. Let's talk about types. We're going to start with structures of arrays. Does everybody know what structures of arrays are? Okay, so structures of arrays is when you, let's say you have a tuple of int short, and instead of having like a vector, you have 2 parallel arrays, one for ints and one for shorts. So this is very common in like game dev, some other high performance things. It's called structures of arrays. In physics, I think, I don't know physics. So how do we vectorize it? Very simple. Like we can, let's say we have a pointer to each of the arrays, and now we can have, we can load registers from them, and we can write our code like that. Unfortunately, if you're just going to do this, you end up in a situation where you have to now rewrite all of your algorithms for 2 arrays, for 3 arrays, for 4. So we have an abstraction. Abstractions that is called a zip, right? Same as standard ranges or Python. You have a special iterator. And when you load from this iterator, you get this object that has 2 registers inside. This is where our biggest disagreement with the standard comes in, between Eve and what the standards do. We say that this object should be wide of tuple, of int short. Why do we say it? Well, first of all, it works. Any operations that you can do on a wide, you can do on this. Do you want to compare them? Yeah, you just compare lane by lane and you mix and the results. Do you want to do shuffles? Sure, you can just swap in each element and just in each register, and it works. It also supports all the nice operations. Can you extract a field? Sure, you can extract a field. I'll just give you this register or this register. No problem. So a standard says, no. We want to be, like, so the standard doesn't have this, but Matthias says that we want to be something else of in tuple and short, like not whatever, SIMD. And we want the SIMD to mean something else. If B, or SIMD of tuple to mean something else, if at all, I'll show you. One of the arguments he makes against wide of tuple is that he thinks that people would have an expectation when seeing wide of tuple of int short, that the tuple go int short together, that they are laid out together in a register. But, okay, let's look at arrays of structs. Now, does this make sense? Okay. Let's look at arrays of structs. So arrays of structs, again, tuple int short. So this is going to be our normal vector of tuple int short. It's laid out. You have int short padding, int short padding. One way of doing it is using operations known as gather. Gather is you take a register from multiple addresses and you load them all together into one SIMD register. So here I would just load all the ints with a gap, right? And then I would load all the shorts with a gap, and I get my wide of tuple. this way. There's an opposite operation to scatter. This sounds amazing, obviously. The problem is there's no free lunch. So you either, if you have this operation in your instruction set, it's going to be somewhat slow. It's usable, somewhat slow. If you don't have it, this has to be done in scalar. So like every element is just loaded. So it's quite expensive. Usually the way it's done is actually using shuffle. So you load a bunch of registers and you shuffle them until you get the ints out and the shorts out. If we do not have this implemented, we're thinking it would be something like load of tuple pointer will return you wide of tuple, and then depending on the tuple specific layout, it will do like the gather operations or the shuffles. Make sense? Okay. Second way of doing it be like something like this. You have the same arrays of structs, so int short padding. And now we're just going to load the register, and we're not going to shuffle anything. And when we want to do an operation on integers, we just mask out everything that is not integers. When we do an operation on shorts, we mask out everything that is not short. And you just mask out, you do the integer addition, let's say, it's fine. And this model is something the standard kind of likes for standard SIMD of tuple integer short. It's a bit of an overstatement. There was a paper about this only for the same types. There's very limited availability. I wouldn't even be talking about this if it's not for standard SIMD of complex. The standard SIMD of standard complex is now in the standard, and it has specifically this model. And I objected because it's kind of like we have one specific struct for which the solution sort of works sometimes, and kind of seems like in isolation just standardized SIMD of complex. Argument from Matthias was that complex is such a built-in type that standard SIMD of complex makes sense in the same way as standard SIMD of a float makes sense. I will say though that in if we have a complex, and when you type if wide of complex, it will give you not this layout, but that other layout. We think that one is better. And also, for the structs, it's absolutely unclear what it actually means. Like, for example, let's say we have 3 integers. And let's say I'm going to do it like this. So this is my first register, and I load the next one with an offset, and I load the third one with an offset. This seems like a reasonable representation of a tuple of 3 integers in SIMD for certain scenarios. It misses half the elements, but it's not bad. But I don't know if this is valid for standard SIMD of structs. Nobody discussed it. They just merged one specific case that is important. On practicalities, when do you want to use what? So mask approach, right, when you just load and do the operation, gives you very cheap loads and stores. And so for something like adding SIMD of complex, this is very good because you just load and you just do an addition. This is your add is just adding for floats. Fantastic. However, everything else kind of falls apart. So for gather, you can do support arbitrary types, and it makes a lot of sense how you support arbitrary types with gather. You get full parallelism of your register. Like, yes, your load is cheaper, but then half of your register is unusable. So this way you get the full register used. Extracting fields make sense. So if you do the must load, when you do extraction, you effectively have to do the same shuffles as you would to just do the gather approach. So, and in extracting fields in gather is very easy. And finally, all the operations just work, right? If you have your values in very different places in a register, then you have an int here and a short here, mixing Boolean results that you get from operations can be quite tricky. I don't know if that makes sense, maybe not. Okay. Any questions about this? This is pretty difficult. I have a question if anybody is awake.
Well, so basically your model is to flatten the tuple, is that, am I understanding it correctly? As opposed to the standard model, which is not.
So my model is to deinterleave each field. and I have its own separate register. And the standard model is, they also want to do that, but they want to call it something else, and they want to standard SIMD to just be one thing which we apply masks.
So can you go back to your picture?
So let's say this one. Okay, this is what standard tries to do for SIMD of complex.
And so, but this is two complex numbers or one?
This is you have a SIMD register with complex numbers. So when you want to do operation on some of them, you mask out the others. So if you want to do on real part, you mask out. You want to do on imaginary part, you mask out the real part. And also when you want to do, as soon as you say in actual C++ code, you say real, it has to shuffle and it will give you out a complete register. So that's getting real out of SIMD of complex is quite expensive. Okay. Yes.
I'm just wondering, how does Eve get the offsets of each member of the struct?
So in Eve, at the moment, like again, it's not implemented. The way I do it is just it's a tuple, and I would just assume you don't do anything fancy. You just give me a tuple.
Okay, but what if it's just like a struct with members?
What if it's just struct? We have an interface that everybody who doesn't have reflection has some sort of horrible interface to give you reflection. Like so, that's we have tuple-like where you have to specify basically what your layout is.
Okay, but I can't just pass in a pod struct and like have it just work.
No, there is a library called Boost. Boost PFR, thank you. So Boost PFR is, I think Anton Paluchin was the original author. And if you want to see some crazy metaprogramming, look it up. So he manages to implement reflection in standard C++, like I think 14, where he decomposes a struct into individual fields.
And in the future, like future C++ standards will give us the reflection that we need so that it would work with pod structs.
Well, and then somebody writes the code, but yes. Okay. So reflection would be good here, yes. Okay. Any other questions about structs? Let's do min element. Min element is simple. So min element, actually these are two versions of min element in Eve. And one is just very simple. Like min is a perfectly valid reduction. Like it's commutative, it's associative. We can just call reduce. If you want to, just call standard reduce. This is actually a good idea in production code. If you just need the value, don't call standard min element, call reduce. And then this way we get the value and we just find it. So we just reduce and then followed by a find, the second pass. Very simple. The second one is like one pass algorithm. Let's look at how that's done. So you have an array and you have registers somewhere in the middle. This is like whatever, in the middle. Right? I'm going to have my running mins. This is my minimum values. Right? And I'm just going to take my elements, I'm going to compare them against mins, and I'm going to update my running minimum values. With the same comparison, I'm also, on top of just having the values, I'm going to also have the indexes, like the positions of the minimum elements. And I'm going to have what is called wide I. So in a normal code, you would write it something like for I equals 0, like, plus plus. In SIMD code, you do the same thing, except you have wide I. So in my case, it's going to be 0, 1, 2, 3. Right? Next iteration, 4, 5, 6, 7. This is our index. So using the result of the same less, we can merge them together and produce the new indexes. Couple of interesting things here. One is that in SIMD code, in actual instructions, calling less and followed by merge is substantially slower than just calling the min instruction, if that's available. So we have like crazy machinery to specifically do that. But the second thing is fundamental, and that I didn't tell you something about this slide. Can you spot what I didn't tell you? There's some important bit of information missing. What I don't say is what's the index type. In scalar code, you just say std size t, right? And it just works. If I do that in SIMD, I suddenly killed a lot of my parallelism because std size t is 8 bytes. And my values will be floats or ints or even something smaller. So in reality, one of the most complicated pieces of code in there is to deal with index overflows. You need to not overflow when the integers overflow. This is why if have min element but doesn't have max element. It's because I don't want to write them. Let's look at the numbers. So this is std min element, and this is the 2-pass solution, and this is the 1-pass solution. So the 1-pass solution is like whatever. Let's look at the win first. So the win is 5 times. 5 times 1-pass solution is faster, right? However, the 2-pass solution is another 3 times faster than the 1-pass solution. What's happening? Yeah. Two things. Like one is maybe there is a code gen bug. Like it's not impossible that there is some instruction generated that shouldn't be generated. It's possible. Like I didn't dig through it like long enough. Right? But generally speaking, yeah, just doing less instructions is good. However, it's a much simpler operation. However, like Peter Cardes, how many people do you know who Peter Cardes is? Okay, I see 2 people. Didn't anybody meet him? It's a shame. We should get. Peter Cardes is a person who answers like every 686 Stack Overflow question. So he had a problem with this benchmark. His problem is like this. If you have a 2-pass solution and your array is not a toy array of 10,000 bytes, but it's actually a big array, by the time you get to the end, you will push out of the cache everything that was in the beginning. So maybe the right answer to how to write min element using SIMD is to split your array in some chunks that would fit in L1 well. And then you kind of remember your temporary points. Few conclusions here. So we looked at index handling. That was the point to talk about min element. It's fairly complicated. You have to do different types, but doable. I complained about how writing loops is difficult. It's again not for each you see. We have to split in chunks. We have to deal with overflows. You cannot just say, now we do SIMD for each. A few acknowledgements. So Peter Cardes is posted here. Wojciech Muller. Had anybody people know Wojciech Muller? Okay, one person. I'm not sure I pronounced that correctly. I'm sorry. So he has his description on 1-pass min. Alex Gutinev implemented min element in MSVC. So if you call min element in MSVC with default arguments, it will be vectorized, and it's a 1-pass solution. The final algorithm. Okay. So the final algorithm is copy if. While copy makes a lot of sense, like you take a register, you load, you store. Fantastic. How do you if? Here we go. There is this notion of compress. Compress, you have a register, you have a mask, and then you take all the elements that are selected and you kind of get them together to the beginning of the register. The rest is something. The reason why I'm saying this is a notion of compress and not a compress function is because depending on the platform, depending on the type, depending on the size, this can be very slow to implement. So in fact, in if we have like a bunch of different functions that all have the word compress somewhere in there, and you use different ones depending on the situation. So here we'll need a compress copy function. It's very similar, except it takes 2 pointers, so an input pointer, or iterator, right, and an output pointer, and then a mask. And then it will take all the selected elements from input pointer and will copy them to the output. And finally, after that, it returns you where it stopped. So if you had this function, do you think you can write a SIMD copy? It's not a trick question.
If you have a mask
Well, you have some predicate to give you masks.
Yeah, and
Okay. Yeah, like you load, test, compress, copy. Load, test, compress, copy. That's the algorithm. There are some variations on the subject. One is called safe unsafe. So the safe one, so unsafe one is allowed to write extra garbage on the end. If you have a mask with the 8 elements, it can write up to 8 elements. The safe one doesn't do it at the price of being slower. The second one is sparse dense. So it's depending on the use case. So imagine if you have an array full of zeros and you want to copy all the non-zero elements, then you would use a sparse version. If you want to write many elements, you would use a dense version. There is a bit of a difference in the interface with standard copy. So this is a standard copy if. It accepts first, last, output, and a predicate. And returns you an output iterator. So the problem, it's perfectly valid for scalar code. However, for SIMD code, we have this problem that if you give me an output iterator, I can never use unsafe compressed copy because it's possible you have a million elements and there's only 2 elements that will be ever written in the output. And so I can never just write 8 elements. I just don't know that I can do it. There is, in the standard, there is this thing called standard par and seek, right? Standard execution and seek. And it's supposed to do vectorized copy if. And this is not something compiler can magic away. So I happened to ask Bryce about it. Like, what was the idea here? Bryce Leibach was leading some of this effort at some point. So he says the idea there is a standard and seek is allowed to allocate. So the implementation for copy if for standard and seek would be you allocate the buffer, copy if there, and then copy to the output. It's overhead, of course, but you know. So if doesn't have to do it because we can change the interface, and specifically we accept an output range. And the condition here is that everything in the output range I can overwrite, even if even if some values there will not be end up overwritten. There's a bit of a thing though. Like if let's say I copy from a million element to like an array of 2, what you would like to know is it will, you know, copy those 2 at some point and then it will stop. So what you want to know is where it stopped. So you would like it to return you not just output iterator, but where it stopped in the input as well. Unfortunately, I just couldn't figure out how to do it well. Yes?
So I believe the parallel range algorithm version of this, which is likely to be in C++36, effectively does the same thing, which is, like you say, it's different than standard copy because of the range itself. And so, like you say, if you've got a big input range and a small output range, you only take whatever can fit. Double check it. But
yeah, I had a conversation with Ruslan, I believe, who was working on something like that.
Ruslan, yeah.
Yeah. So what I didn't understand from that conversation is, am I allowed to overwrite anything in the output range? So let's say my output range is 5 elements and I end up copying 3 elements. Am I allowed to write all 5? Because I say yes.
I think no.
If that's a no, then it's not helping. I need to be able to write all of the elements.
Okay, I'm going to have to check to find out. So we'll find out before the end of the next time.
No worries. Okay, let's do numbers. This is standard copy if. Benchmark works like this. It's 10,000 bytes. It's the same 10,000 bytes. Elliot, don't tell the answer, people. You have, on the left, no elements are copied. On the right, all of the elements are copied. This is like 80% of the elements are copied. Looking at this benchmark, there's something weird about it. Can you tell me what?
What happens in 95?
I don't know. But like a fluke, we can talk about this after somebody tells me what's wrong with the benchmark. if you have elements to copy, and you copy, which use case would be the worst? You copy no elements, you copy all of the elements, you copy half the elements. What's the worst case scenario?
Half.
Yeah, that should be half. This is benchmark for shorts. And on shorts, it's very clearly half, right? What's happening? Well, it is 10,000 bytes. My computer can remember that many branches. So the branch predictor just happens to remember through the 50% random elements here. Like, and on shorts, it doesn't.
So it's a cache, basically. Like,
Branch predictor I don't know. It's not it's a branch predictor. Branch predictor remembers where you jumped. I don't know that
you
much
just kind
about.
of run out of. Yeah, I see.
My understanding of branch predictor is very limited. Let's not go there. Okay, let's look at SIMD stuff. So this is a default one, and here we get whatever we have two, like whatever 1.5 point faster here. On the right, we have about 3 times faster. This is a sparse version that assumes very few elements are copied. And you can see that on 5%, let's say, only 5% of the element is copied, we get about 3 point something times faster. And obviously, it gets worse. It's designed to be sparse. When you copy 50% of the elements, that's hardly sparse. For the shorts, where there's more elements, so no, okay. You get about this is more than 10 times speed up. If you copy half the elements using SIMD, this is more than 10x improvement for shorts. This is, for example, like you would think, why would I copy more than half the elements? That's what sorting does. Sorting, hopefully you got the pivot and you copy hopefully half the elements. It's pretty good. Here we have about 2 times speed up. On the left, the branch predictor just made the difference negligible. For the sparse version, let's say for 5%, we get another 10 times speed up almost, right? So 5% of elements copied 5 times faster. And even because the branch predictor doesn't help the scalar version so much here, as a sparse version which does have less branches, falls off much slower compared to what we saw before. Any questions about the benchmarks? Yeah.
What are kind of the implementation differences between the sparse version and the regular version? Like
let's talk in the after everything else, because that's a lot.
Sure.
So what's about the standard? The standard has this function. It's not merged anywhere. There's a paper. That paper has a function called compress, and it returns you a SIMD. The problem with this function, as I mentioned, like either you can implement it well or you cannot implement it well. And if you cannot implement it well, you shouldn't use it. So if you use this function, you should know whether or not it will be good for this size, for this type on all of the platforms you have. For this specific case, we would suggest something like unchecked compress store. So you take a mask, a register, and an output register where you write, and return an iterator. So you instead of producing a register, you produce memory where you wrote. This one can be implemented pretty good everywhere I tried. I have numbers. 2 conclusions here. So we learned about the compress stuff. We see again that copy if vectorized has a different interface from the standard copy if. So you have to it's again not a for each. So inside of copy if, there's 2 loops, one for when we can use unsafe store and one we cannot use unsafe compress store. A few acknowledgements here. So the main way we use to implement the compress, that's to the question of how they're differently implemented, is using tiny lookup tables by Stack Overflow user Akrit. I don't know his name. Does anybody know him? No. He did a lot of good stuff on the internet. So it's like 27 registers stored in memory. Really, really clever. BMI2 solution we use when that's available, proposed by Peter Cartes. We have, for really weak architectures, we sometimes use switch and shuffles. There's a switch table. And finally, we have also SIMD scalar approach in the mix, separately proposed by Peter Cardes and Ilya Albrecht. That's mostly sparse, to your question. It's kind of, it goes through all the matches, and if there is very few matches, it's a very good idea to do.
Is it sort of like a sparse matrix? Is it kind of the same? Like
No. I have some slides in other talk I can show
Sure.
you. Links. So there's a slide. This slide is tinyurl.com at JFDY 2025 part 1. The next one is the same but part 2. If you want to see some algorithms, like if you didn't care about the interfaces stuff, I did a few talks. So there's a talk called My First SIMD. Ideally, you find the blended C++ meetup version. There's a talk called Advanced SIMD Diagrams and Pictures. Ideally, meeting C++ version. And finally, this year, I hopefully will present somewhere a SIMD substring in a string, where I just talk about search for an hour. Some of the things intersect because you need to go from scratch, but some of the things are different. Okay, was this any questions? Because that's the end of part 1. Yeah.
So the answer to your question is that the effects of the SIMD copy or the ranges copy in parallel require only things in the result plus n, where n is the number of matches are overwritten. So that indicates that it cannot write past n.
So it cannot, if you give me an output range of 5 elements, I cannot write all of the 5 elements.
You can write all 5 elements if there are 5 matches.
Okay, so unfortunately, I believe that the best you can do with this interface requirement is to allocate a temporary buffer where you would be copying if first, and then copying to the output. That doesn't seem ideal.
Wait, couldn't you just branch on the size and use the unsafe version until you get close to the end?
You don't know. So the problem with that unsafe version. So okay, let me go to the slide with unsafe, and I will show you.
Also, you don't know the size because you have to do all the comparisons to find out how many elements are you going to copy.
So okay,
Like
so
you don't know, like, are you going to copy 10 elements?
Oh,
or
you
20?
don't know the outs. You don't know that, right? The outside. Yeah.
so I don't know what that conversation was, but I will try to answer it myself. So let's say I have a register that I loaded, and 4 elements in there are selected. So it is possible that this was the last element written ever. Right. But what the unsafe did, it wrote 4 extra elements. Just whatever garbage was there, because this is fast. Oh. Okay. Anything else?
Well, I guess I'm not following your statement though, because you know where the boundary is ultimately. So when you make the copy from the register back into the range, at that point you only need to copy.
So this is I'm not following. Sorry, can you say it again?
Okay, so you're saying that you can't use the sort of unsafe version without maybe an extra buffer. But what I'm seeing here, right, is and maybe I'm misunderstanding what the picture is talking, but you can use the unsafe stuff in the register itself, and when you know where the bounds are, the 4 good elements, then you're just going to copy those into the output.
It's not a copy. It's so okay. Let me just say on something very modern, like let's say latest Intels, you have a compress instruction. The way to implement compress copy unsafe is you compress and then you store. That stores all the register. And then the way to implement a safe one would be to use an instruction called compress store, one instruction, compress store, which doesn't write extra stuff, and that is slower.
I see.
Yeah, so basically you would have to do compress store over and over again. On IBX 512, you might be able to get away with it, given what your computer is, but on previous stuff, no.
Why would this be unsafe? Isn't it only I guess, isn't it on to the person calling you to make sure that they're supplying data, like a destination and out that has enough space for it? It only really matters at the very end.
So you are absolutely right. So compressed copy unsafe will write more elements than selected, right? So your job to provide 8 elements to write, even if there's 3 elements selected. The question is, that's why it's unsafe, because it will write more elements that were selected. Maybe unsafe is not the word you want.
Yeah.
But do you want to?
Oh, okay, yeah, I can envision that. I can see what you're saying.
Yeah, so we write more stuff. The problem with copy, if Mimi and Jeff understood correctly what it says, is that it provided you 5 elements in the output buffer, but you're not allowed to write 5 elements, so it's not helpful. It will help you to prevent a crash, but it will not help you to vectorize.
Well, I mean, again, it's still going to be a vector instruction. You're just saying it's going to be slower, right?
On very modern stuff, on like latest stuff, like on I am on my work machine. No, on the things I have in production, no way.
I wouldn't worry by the time this is implemented.
So that's an interesting conversation that we have in the second talk. This is, by the way, I'm happy to let people go to have a break, to try to wake up, to decide if you want to come back. I would love to have you back, but
Actually, even very much, because I think Intel in the E-cores, I think that they got rid of AVX 512, if I'm not mistaken. So that means that like even
that conversation, I don't know. I don't understand E-core. So okay, this is the Intel thing. IBX 512 is a family of instructions that's like super modern Intel stuff. There is like actually 1 million difference of those. Now we're finally getting the real thing. Like for example, I bought myself a AMD Zen 4 at home. It was for some like $300, and it's fine. It has a full IBX 512, like at least working on paper. So it's a lot of silicon to support those instructions. And so what they decided to do is that Intel has like different cores. You have E cores and you have P cores. I feel like take a big grain of salt to everything I say. On the E cores, E cores are small, energy efficient ones, and they don't want to provide those instructions there. But now you're in trouble because none of the threading systems kind of support this very well. So the only way, if this is the case on your processor, if you try to use an instruction that's not there, your program crashes. So now the only way to actually do it is to pin, is to pin your core somewhere. Maybe, I don't even think you can do it at runtime to check, because if you check at runtime and then somebody suspends and reschedules you. It was a big story. So they first added IBX 512, then they removed using a patch. So for example, when we wanted to test Eve on IBX 512, we had to buy an old Rocket Lake CPU, an older one, because a newer one didn't support the instructions we wanted.
So I think the point is that if you have AVX 512 or SVE, which is like the modern stuff, then you can do a predicate store and you can like sort of be okay with only the safe contract. But if you have AVX2 or Neon, which is the old stuff, Neon is in every phone, right? Like phones don't have SVE, they only have Neon. Then you cannot vectorize unless you can overwrite. You have to overwrite.
New phones have. Sorry, this is just a long. Anything else? Yeah.
If you know the size of the output buffer, you could store the last register, or you could load the last bytes into a register, keep it around forever, and at the end of your loop, you just restore it back into.
That's a very good conversation that I had with some other SIMD people about masked stores. So what you're doing there? So the comment is what if we stash the ending? First of all, you need to stash the whole array. because it's not just the ending. You need to stash all of it.
You actually need to keep like a running stash as you go along of like always the next 16 bytes.
Yeah, so the question then becomes, is that legal? Because what you do is you just violated thread safety. You introduce a right that was not there. In here, it's so like you load the register. So it's load, replace, store effectively, right? There was a time when, for example, booleans would be written like that. You load the boolean, like instead of loading a boolean, you load an int, replace a bool, write it back. And C++11 made all of that illegal because now we guarantee thread safety on adjacent boolean values. Like, so you can modify, you have two boolean values next to each other. You can modify one, modify the other. They will not affect each other. Like with bits, you can no longer do it. You cannot do it, but with bools you can. And if you try to do the monitor, then now you're saying that that value past the end was okay to overwrite temporarily, and I'm not sure that's true.
I mean, you could maybe assume that if you know, like, if they give you two buffers or 2 pointers for the buffer, like start writing here, end writing here, then you can assume that like that range you have exclusive access to.
That or just have access to. Like, you know, I just assume I have access. You gave me a range I can write there. Like that was my assumption.
I mean, you know, it's just a matter of writing the words.
Yeah, but so like I'm very appreciative of people who are willing to do that. That sounds miserable.
No. What I'm saying is literally you could change that effects clause, and what you're suggesting would be perfectly legal. And you know, it's a design choice, right?
Yeah.
This is a design choice, and what you're telling me is that yeah, there's a lot of processors for which that means essentially you're not going to get this, you know, capability. It's only on, you know, some of the latest. Now, you know.
So just so we kind of, I appreciate everything. So just for context, I'm going to remind you, if it selects a slide, we're talking about a 10x difference performance.
Yeah, understood.
Like so I would like that.
No, I understand, and so would I. But you know, it's a question of at some point, you know, you're gonna maybe. I mean, these instruction sets are not going to be reducing in the future, right?
I suspect so. Yeah.
They're going to be inclusive. They're going to be continuing to expand.
That's a very good question you're raising. So one of the things would be cool, because the standard has, in the second part, we'll talk a little bit about that, and I'll show more. The standard is a bit inconsistent about what it's trying to target. It is cool to say, hey, we, as you said, this will be in production in 10 years. Right? What do you care about in 10 years? Game developers say we still care. They still care about, like, the Helldivers 2 had written this kind of scandal when they tried to use IVX2, and some people complained that it doesn't work on their machine. I don't know how that happened, but that's the reality of it. So, okay, if you want to support the modern stuff, go for it, and then you get nicer interfaces and you get more powerful APIs. You cannot do things like WebAssembly, but WebAssembly is maybe changeable as well. But if you settle on that, cool. But there are some other things in the standard that clearly designed for older stuff. That are not relevant on anything modern. So,
Yes.
so it's inconsistent.
The standard, you mean?
No. I mean the SIMD.
Oh, the SIMD. Oh, sure.
Standard SIMD has specifically, I mean, a line flag. Matthias doesn't quite. We have a line flag in the second part, but Matthias doesn't quite agree with me on that. But my expectation is that the line flag would not be beneficial to you on modern platforms very much.
Right, because basically unaligned load got as fast as aligned.
I will talk about that. Do you want to know about unaligned loads? Come to the second part. Okay, let's go get tea. Yeah.